Thanks very much to PyData for inviting me, and thanks very much for coming, even though I know the match is on. My talk is about digital image processing. So it's an area that I got into in my PhD and postgraduate studies. I think that there's a lot of interesting material in the area, in the whole field, that's really good for looking at signals and any kind of signal processing. So fields such as seismology, econometrics, speech recognition, and then bridging out from signals to images in 2 dimensions. This is applied in like ultrasound, computer vision, so machines and robot vision, and satellite imagery, which is where my PhD studies came in, with analyzing images from satellite observations. So the image I put up right now is of a handwritten digit 8, and it's flicking between the actual pixel values on the image itself. And so you can see that we're looking at things like noise in the image and different, different values. You know, the 8 isn't just a consistent signal around it. My postgraduate and PhD studies were on the analysis of satellite imagery. This is an image from the SOHO spacecraft, and it's an image of the sun in the center, represented by this white circle, and an occulting disk that blocks out the brightness of the sun and its immediate atmosphere. And then the surrounding material is the corona and beyond, and we're looking at a coronal mass ejection, which is an eruption of plasma and magnetic field. So the drop-off in intensity in this image is massive because of the brightness of the sun that's dominating. And so image processing techniques are used to do things like correct for that intensity drop-off, distinguish the features that we're interested in, such as characterize the structure of the CME itself to track its evolution, but suppress the background, suppress the stars. Sometimes planets move through the field of view. So this is where my foray into image processing came about. And so in analyzing the images, this is kind of a snapshot of what we would attempt to do by taking these 2-dimensional observations and analyzing them from 2 different points of view here. So this top image is showing a snapshot of the inner solar system, where we have Earth, the 2 stereo spacecrafts now on either side in their orbit, a couple of other planets and the sun in the middle. So when they image coronal mass ejection, we see stereo A's observation on the left and stereo B's observation on the right. And so we're analyzing this image from 2 points of view, and that's a plane of sky projection that we're trying to characterize the structure and step it through time to understand the evolution of that material as it propagates through space. And so one of the models that we apply is elliptical tie point, and using those, the kind of like confined solution space based on these observations, and build a model to try and get at the true kinematics and morphology of this eruption. And so this is where the kind of pipeline comes in of working from these 2D observations to building up 3D observations, or 3D models that can kind of constrain the physics that we think is happening. Now I'm working at Royal Mail, and I'm working as a data scientist in the team there. I went through the Pivigo S2DS program, and Royal Mail is a vast company with amazing amounts of data across the network of the UK that's been gathered in the last 500 years of the business. And they've built up a data science team to use our various skills to analyze the data that they have for a multitude of projects across the business. So, for example, some of the projects can involve the marketing side, churn, customer segmentation, looking at systems, recommenders to our business customers, for example, delivery windows. We're electrifying the fleet, and we want to optimize routes, generate sales, and of course forecasting mail volume across the network of the UK. So it brings together a lot of different skills, and we have a team of various scientists from different backgrounds, such as biology across to physics. And all these different skill sets come together to kind of build that unicorn team. And one of the areas that I'm exploring today with you is digital image processing as a field where inherently what we're trying to do is detect feature X as distinct from environment Y. So any researcher may be interested in this across any of these disciplines. And the kind of things you're going to look at are noise in your signal. So if you have a signal at the top here that you want to study, this is the ideal signal, and there's various levels of noise that are involved. In images, you may want to look at structure from butterfly imagery right up to, I think this is a nebula structure. Motion through time steps of the images, so here's two moving objects, vehicles, for example. And characterizing the things that you measure in the image. So, for example, facial recognition, so modeling a face with an ellipse here, or modeling the movement of a hand and the fingers by other elliptical structures. And one of the big things is to overcome human error and bias. So you want to be able to make things reproducible by building an algorithm that can analyze the images or the signal. And so that's both reproducible and overcomes one observer maybe looks at something in one way and another looks at it in a different way. Many of these kind of techniques may have been seen in some like social media nowadays, for example. Snapchat, there's different filters that can be used, detect your face and put a mask on it. Facebook, they have the tag my friend. Instagram, all of the different filtering that happens. And Photoshop, where you kind of get to play with a lot of these techniques yourself. So the field of image processing pulls together a lot of different domains. So your math, stats, and physics comes together with your optics and the signal processing domain. But on the other side, you're looking at machine learning and like recognizing patterns and building that artificial intelligence system to ultimately feed a computer to understand how to interpret the images and make decisions about what's happening in an image. And so I've put this together to just show some of the steps, and I'll go through some of these where you have the acquisition of the image, you manipulate it somehow, you segment different parts, you want to represent things in the image so that you ultimately get that understanding, and that's your output depending on the object or field that you're in and studying. So digital image is a sample 2D space in regular grid. So this is a grid that's like the first image that I showed with the figure 8 in it. And so you're quantizing that grid, and this is your pixel space that you're building up. And so that's how you're representing the image as this matrix of integer values. But that human bias that I showed you is something that's important to acknowledge. So if we have a stepwise function and you're representing that as an image, that's the actual illumination stepwise, but the perceived brightness of the image, you can kind of see the gradient that seems to be across each of the lips in that in the top image. It's not actually there. So we're overcoming that bias that the humans have. And if I show you this, the background has a gradient along it, but the inner rectangle is actually the same shade. Does anybody not believe me? So you can kind of see it there. And of course, we see this all the time in optical illusions. So you as a human want to say there's a white square in the top left, or that shape A is actually smaller than shape B, or there's no way that those lines between the stacked cubes are parallel. And I want to ask what color that dress is. To me, it's blue and black. Does anybody not see it as blue and black? Yeah, so you may have seen this as a phenomenon that went viral over a year ago, I think. So image processing is kind of understanding this and getting a computer algorithm to understand how to transform the domain and the range of the image. So if we have the image of the Terminator here, you can represent that by the value of those pixels and move that around and interact with it in that kind of a format. And so the key stages in that digital image processing kind of pipeline, you can work from your problem domain, whatever that may be, any researcher in any discipline. You've somehow acquired this image. So for me in astrophysics, it was a source system being the sun, illuminating a coronal mass ejection. We have an optical system on a satellite, and that's realized by this digitized output. Image enhancement, we've heard before about contrasting images so that the human eye can best see things. It's the same with the computer. You kind of manipulate those values of the pixels so that you can best characterize structure in them. Morphological processing is kind of the growing and thinning of the pixels. So here there's an example of a fingerprint and different mathematical operations on how you grow out, this is a binary image, grow out those white pixels or shrink them. You can reduce the noise, or you can also join up parts of the fingerprint that are actually one part of the continuous loop. Segmentation is separation of parts of the image, such as the feature, the object that you want to look at. So the distribution of the pixel values, you see a clear separation in this very kind of clearly separated image, so that you can take this, I think there's some sort of a crowbar, take them out without the background and the shadow is gone now. And then how you represent that and describe it based on this quantized space that you're working in. You build up a picture of what's actually being realized in that digital output. And so these are two ways to describe the feature that's being observed in that pixel space. And when you have all these measurements, you've described what's in the image, you can move into recognizing objects. So this is a snapshot from the iris data set where the length and the width measurements that you would have gotten out can be used to cluster and identify the different objects, so the different plants in that data set. And this feeds into computer and machine learning. So an example here of detecting all of the pedestrians that are moving and realizing whether they move in or out of a storefront and counting the volume of people, essentially, that have been inside or outside of a shop at any point. And we see examples all the time in deep learning, especially nowadays with classifiers of images. So if you want to input an image of a dog, that's a load of pixels that's thrown into that deep neural network. And you're looking at these combinations of the edges that are identified. So there's a filtering process happening here to pull out those edges and how they interact. And they all build up this feature space that you're working with on top of your labels to find that best fit to classify, oh yeah, there's a dog in this image. And so this is really important for robotics and AI, and getting it right and overcoming that bias. And we see articles nowadays as well that we're inherently putting our own bias in how we train models and features. So we've seen that real simply with the optical illusions. And so autonomous cars is a really important place to get this right. And so I have a quick notebook of some examples that I put together of these steps. If anybody wants to work along with me, you can download it from this link, or you can download it later. It's in a Dropbox. And then if you like what you see, please feel free to contact me on LinkedIn or Twitter. And I have a blog, datascienceunicorn.com, that also tweets out articles of interest and resources for data scientists. So I'll just move to the Jupyter Notebook. This notebook essentially builds off the skimage module, which is really nice. A lot of the work that I showed you that I did in my astrophysics studies, I worked in a code called IDL, and we had to kind of build up a lot of what we wanted ourselves. Nowadays, there's loads of nice inbuilt functionality in Python. So some of the examples I can step through here, and I'm not going to live code, I prepared this before. So loading in the skimage module, and then you can load in an image of interest to you. So I'm going to load in an image of a stamp, because I work at Royal Mail. And so this is a grayscale image, because it's so much easier to work with. Color image, you have to split out the different color levels. Yeah, question? Sure, sorry. Thank you for pointing that out. Yeah. And so when we plot an image, you may obviously be first interested in looking at the histogram of that image. And so you can kind of see straight away that there's 3 layers to this image. The histogram and both the image kind of convey this. So the bust itself, the background is dark, and the letters of the first class postage. This is a noisy image. If your image doesn't have noise, you can add noise, because There's always noise in the real world, I guess. We may want to enhance the image somehow. So I look here at changing the distribution. So here's the low contrast image, and we have the histogram and the cumulative histogram in red. Contrast stretching, we stretch that out because we have all this unused space here. And you get a better contrast of the background against the image that you're looking at, which in this case is the bust or the first. And then histogram equalization is a technique you can apply, and adaptive equalization, another one similarly. So ways to manipulate that histogram value to isolate parts of the image that you may be most interested in. So this is your contrast enhancement. Clipping the image based on that. What we saw about all of the histogram pixel values were sitting in an upper range. Clip that so you're actually getting a better contrast without having to worry about stretching. It's just a hard threshold. I've put this color filter on now. Interpolation, so this is a way of smoothing the image. So a lot of the noise in an image is grainy and it kind of basically hot pixels around the image. You can apply an interpolation, so smoothing the image based on its nearest neighbors. So bicubic interpolation is applied here, and you can see that it smooths some of the detail as well, which is a side effect, but you've smoothed out a lot of the noise. And later for things like edge detection, that's really important because your hot pixels will go mad when you're trying to isolate edges in the image. So you need ways to suppress them. And this is one fundamental way. There's cool ways in different types of wavelet transforms and things you can apply. I don't know why I inverted the image. Just different ways to represent things. Different people may look at it in different ways. Segmentation, what I talked about briefly before. So here I've just arbitrarily drawn lines to say, okay, I think this is the background, this is the body, and this is the text. So you can clip each of those relative to the pixel values in the image that you're interested in. And intensity contouring. So all of these hot pixels are kind of getting contoured based on the, whatever I've set it as here, I think a half. So this image is normalized between 0 and 1. So we've outlined the letters, outlined a contour around the whole body, and outlined the border of the background. So you can kind of see how we're getting towards detecting the objects in the image. And so clipping that again, you can set those thresholds, again, just hard thresholding here, segment the image, and now we've got a flat representation, 1-0 of your features of interest versus the background, for example. And then, if I'm going over time, please shout at me. The edges, you can apply, basically a derivative is what a lot of edge detections fundamentally are based on. So applying a derivative, you get the rate of change in the image, so steps in your intensity of pixel values. So you can outline the imagery in a way like this to get the picture. And then there's nicer ways where you apply a smoothing as well and draw the pixels around the edges by a chaining method to overcome both the noise and highlight what you're interested in the image. So we're getting at the edges at this point, overcoming that noise. Using wavelets here to denoise it. And again, you can see the side effects. And there's cool ways nowadays. This is just me demonstrating simple packages. It makes it so easy for us to understand some of the ways we can manipulate the signal for our own interests. And morphological processing. So here we're looking at ways to represent the images by thinning and dilation of those pixels. So you kind of build up this skeleton here, you've thinned it out, or just partially thinned, you get this real nice detail around the pixels of interest. And I think this is another way where it applies two methods, this medial axis method of thinning the pixels into a main kind of spine within the space when you close it in. and then it's put the image contours over as well. And you can see where like things like image compression kind of come in here, because you're dropping out a lot of signal you may not need.
What does color mean here? Because you started with grayscale and...
Yeah, I think the color here is from the distance that you've thinned into the center. So like you can see like it's kind of like just thinned a little bit here between these pixels, so it's a purple, but it's thinned a lot to come into this spine, if I remember correctly. But we can revisit that and play with it. And yeah, this is the dilation as well, so a real boxy version. Yeah, so I hope that this has been enlightening with some of the like processes that are really easy to play with and nicely built into the Python module, but it helps us understand a lot of the functionality and capability behind processing signals for features of interest in whatever your field of study may be. Thanks very much.
We have time for a couple of questions.
Yeah.
Who's doing the question?
So I was just going to say that I think Microsoft
There's a microphone
should work.
in front of you.
Okay, sorry. Question is, I think this is fine for black and white, but having tried to do deep learning on color images with a lot of in-context features, do you have any sort of suggestions for, out of this, the best set of transformations for color? Because obviously this is all weird. What would you do with the color image, really?
Yeah. It's a really good question, and it's very valid nowadays. You can, it depends on how the image is generated, but a lot of images are generated based on the RGB scale or YMCK. So inherently, it's 3 images combined together, and so you can process them as a cube of images and work in, like in Fourier analysis, you'll work in K-space. You can kind of look at images in that way and consider these as other dimensions. So when I talked about the dimension of time and time steps, that was one example, but you can build out your cubes of images based on that level of knowledge. That's a possible suggestion, but it's a really valid question because there's a lot of exploration on what to do with those levels of details. My PhD studies were all on white light imagery, so yeah, I was like, great, this simplifies it in the first instance. Do you pick? Or?
Go ahead.
Just could you chalk up the link again? Because I didn't.
Sure.
Cheers.
Yeah.
I was just going to ask more about the problems you're working on at Royal Mail. Do you use that stuff? I mean, in particular, you maybe can tell us a bit more about the data science tasks that you're currently doing. Or if it's confidential.
Yeah. Part of what I work on is confidential, but you can see how, like, I showed one example of churn modeling, and we're looking at the signal of the mail traffic and volume, for example, across some of our business customers. Processing that signal is a realm of signal processing where it's really noisy. We're looking for patterns, looking for trends. I thought maybe Fourier analysis would be nice because in the first instance, if we can like smooth it out enough, you're looking at different rates of behavior for different customers, and that kind of leads into segmentation or different ways to label them. The optical character recognition system is something that I've been interested in. So a lot of the handwritten letters still have to go through a manual sortation, but most of the print letters get read by the OCR, and so that can locate the postcode and read it and understand that it can digitize it and then digitize like the parts of the address in relation to the postcode. But I'm curious, are there ways to enhance that based on like training what we've labeled essentially by, you know, gathering all of this handwritten post. And I've heard at like Christmas and Valentine's, it's especially hard to read red envelopes if somebody uses black ink, for example, and they all get churned out for a manual read. That's the color question again. So it's interesting. Yeah.
Was one more question somewhere over there. Yeah.
Sorry for shouting it out at the beginning. But I'm more interested in the PhD topic. You said about the images that you took onto satellites. Is there a concern when I assume satellites move really, really quickly. Is there any concern when you process both images that took at the same time? This is a relativity problem, or image sort of overlap a different way than you're expecting it? Or is it all sort out because the satellite is running really efficiently?
I had a joke with one of my friends that my PhD is actually really easy because my error bars are plus or minus the sun. But your question is perfectly valid from the point of view that we want to ensure we're capturing our images at least in the same cadence with regards to the processing on board and the downlink of the telemetry. There was ways to overcome that, and Stereo as a mission was built to make sure that they were capturing at the same time and considering the lag at any point. And then because they were imaging such large-scale phenomenon, we just kind of account for it in the errors, but the time offset wasn't the biggest issue. It was that one pixel was such a large distance in the heliosphere.
One last question at the back. Yeah.
Just a quick observation. Is the answer to the red envelope question ditch the visible spectrum and go UV, or does that tend to work?
Yeah, definitely. I mean, one of the medical applications was MRI, for example, so you can use any...
Specifically work for red envelopes in black ink?
Oh, yeah. So that's why I'd love to get under the hood of the OCR and say, okay, what are we doing here? You know, is it the same as what we used in the CCD imagery for satellites, white light imagery, or is there something else that's going on? How expensive is infrared versus just trying to build off the current system? You know, all these questions come into play. Scientists, I just want to see what happens.
Okay, let's
Great.
thank.
Thanks very
one more
much.
time.